Okay, part 2 of lecture 9. So we talked about in part 1 about integer powers of these polynomials, areas under this particular polynomial or under this particular curve 1 plus x, and we talked about the integer powers, positive and negative. So now the question is, what can be said about the rational powers? So what about rational powers? Okay, so for this part, he considered the areas under the following sequence of functions. So Newton considered areas under the following functions. Under the powers, the rational powers, under the rational powers of 1 minus x squared. 1 minus x squared. So we're not talking about the function 1 plus x here, but 1 minus x squared. So he wanted to know rational powers of this. What would they look like in terms of terms? So he can write out an expansion for these rational powers. Okay, so he considered the following. This is the line y equals to 1 minus x squared. Okay, so the zero power of that, so 1 minus x squared to the power 0 is equal to 1. So that's the line y equal to 1. What about y equal to 1 minus x squared to power half? This is the same as saying the square root of 1 minus x squared. Okay, or y equals to not 1 over 2, but now we have 0, 1 over 2. What about 2 over 2? 2 over 2 is the same as power 1. So 1 minus x to the 2 over power 2 over 2. That is the same as saying 1 minus x squared to the power 1. Okay, 1 minus x squared to the power 1. Y equals to 1 minus x squared to the power 3 over 2. That is the expression itself, not the expression for the area, would be the same as writing 1 minus x squared times the square root of 1 minus x to the 2. Okay, this is the sequence of functions that he considered. And y equals to 1 minus x squared to the power 4 over 2, which is the same as 1 minus x squared to the power 2. So in this sequence of functions, we see some integer powers as well, and they obviously can be written as rational powers. For example, this is an integer power, this is an integer power, this is an integer power, and so on. So once again, just like before, he wrote down the expressions for areas of integer powers because those he knew. So once again, we write the expressions for areas under areas of integer power of curves that look like this: 1 minus x squared to the power p. So the integer ones he knew he could find those using the same rules as in the previous page. So why don't we just fill the table first with those, and then we worry about the rational powers. So first, let's just do some expansions. So for p equal to 0, we have area using Pascal's triangle, area under 1, and that is equal to x. For p equals to 1, we have area under 1 minus x squared. Integrating each term, we will get x minus x to the third over 3. For p equals to 2, we have area under 1 minus x squared, the whole thing squared. If you expand that and take and integrate term by term, so that would be area under 1 minus 2x to the 2 plus x to the 4. Again, you can use Pascal triangle to write the expansions. Then this area is equal to x minus 2x to the third over 3 plus x to the 5 over 5. P equal to 3 is the area 1 minus x to the 2 to the power 3, and again, if you expand this using Pascal's triangle and integrating term by term, I'm not going to write the coefficients because I already told you how to do this. I'm just going to write the final formula for area. We'll have x minus 3x to the 3 over 3 plus 3x to the 5 over 5 minus x to the 7 over 7. For p equal to 4, p equal to 4, we'll have area 1 minus x squared to the power 4. That area will turn out to be x minus 4x to the power 3 over 3 plus 6x to the 5 over power 5. Minus 4x to the 7 over 7 plus x to the 9 over 9. Let me just write one more for the sake of it. So p equal to 4, I have area 1 minus x squared to the power 5, and that would be x minus 5x to the 3 over 3 plus 10x to the 5 over 5 minus 10x to the 7 over 7 plus 5x to the 9 over 9 minus 1x to the 11 over 11. Again, the numerators and denominators, well, the denominators are in arithmetic progression, and for example, this is 1 and 3, so their difference is 2. This is 1, 3, 5, 7, 9. Again, the difference between each number, consecutive number, is 2. 1, 3, 5, 7, 9, 11, same thing. So the denominators here are in arithmetic progression, and all the coefficients of the terms obey the Pascal's triangle as mentioned before. So now we're just going to put on the table the ones that we already know, and then we shall take it from there. So I'll write denominators. Are in arithmetic progression. And numerators, coefficients, that is, numerators obey Pascal's triangle. Okay. All right, so let me fill in what I can deduce from here so far. So minus 1, minus half, power 0, power half, power 2 over 2, which is 1, power 3 over 2, 4 over 2, which is 2, 5 over 2, 6 over 2, which is 3, oopsie, 7 over, this is, yeah, so I said 6, yeah, and then I have 7 halves and so on. Okay, and looks like the terms are as follows. So the terms that appear here are of the following form. You have, certainly their signs are alternating, so that's what I'm going to write on the table as well. So the first term for all of them is x over 1. So the second term for all of them is minus x to the 3 over 3, minus x to the 3 over 3, minus x to the 3 over 3, x to the 3 over 3, ignoring the coefficients for a moment because that's where I'm going to write the coefficients of the terms. So the next term that appears here is x to the 3 over 3. And then the next one would be plus x to the 5, what am I saying? Yeah, so x to the 5 over 5. The next one is minus x to the 7 over 7, minus x to the 7 over 7. The next one appears to be x to the 9 over 9. And then I have minus x to the 11 over 11. And then we can write, let me not just do this. We'll just complete this so far. But okay, so let me fill in what I know. So for power 0, where am I? Power 0. Power 0, this is area. Area is x. So for power 0, area is x. Area is x, and the coefficient in front of x is 1. Okay. Power 1. Power 1. The coefficient of x is 1. The coefficient of minus x to the 3 over 3 is also 1, and there are no other terms. So I will write 0 for that. Looking, by the way, for power 1, I only have one term. The others don't appear, so I also write zeros here. So for 2, p equal to 2. Coefficient of x is 1. Coefficient of minus x to the 3 over 3 is 2. Coefficient of x to the 5 over 5 is 1, and there are no other terms, so I write 0. For 3, so 3 is here. Coefficient of x is 1. Oops. Coefficient of x is 1. This also will be 1, but let's ignore it for the moment because that's not what I'm doing at the moment. I'm doing the integer powers. So coefficient of x in the third power is 1. Coefficient of minus x to the 3 over 3 here is 3. Coefficient of x to the 5 over 5 is also 3. And coefficient of minus x to the 7 over 7 is 1. And there are no other terms. So I have this so far. Now, let's just look at this for a moment. I have to work at first with the entries that I have. So here, let me just write, note the following. Each entry, so far, each entry, and I'm going to use that to complete the table. Each entry is the sum of the entry 2 spaces to the left, is the sum of the entry 2 spaces to the left and the one above it, and the one above it, the one above it. Okay, To fill in the missing entries, so Newton devised another system, because it's very hard to say now what should it be in this other missing entries. Oh, by the way, so for -1 I can also complete, although I shouldn't, let me just leave it alone for a moment. So he devised a slightly different system by using the known entries on a row to generate some systems of linear equations whose solution would complete the rest of the row. So here's what we do. I will need a new page for that. But I will need this. So, lecture 9, page 3, part 2, continues. All right, so what did it do? We are going to, so the method that I will derive is in general, and it should work for absolutely any row and any entry. So we'll start by doing the following. So to fill in the missing entries, we do the following. Okay. We start with some, of course I'll do an example. We'll start with a constant sequence, of entries. Let me call those A, and so on. Okay, and I'll start with some constant sequence of entries, and then some random row, and some arbitrary left, not row but column, I meant to say column, and some arbitrary left-hand column. All right, before I move on, we want to devise a way to fill in the rest of the entries. So keep in mind, a table like this could go indefinitely on both directions. So to devise a general method, it makes sense to speak of a constant sequence row. So in this table, I will start by considering a row whose entries are all the same constant, for example like this one here, and I'll pick some arbitrary left hand column, maybe this one, maybe this one, maybe this one, I don't care, it doesn't really matter. The bottom line is that we start with some left hand column. So for generality, we call, let me just do a little table here. So I have A, okay, and some arbitrary A, B, C, D, E. These are all entries. This is your arbitrary row. Okay, for spacing purposes, because I'll need the space. Okay, so here's my constant sequence or constant row and some arbitrary column. All right, so I use this rule for example, for this next entry. This next entry will come from adding A plus B. So the next entry below here will be A plus B. And the entry below this A would be A plus B, or 2A plus B. The third entry here will be A plus 2A plus B, or 3A plus B. And the fourth entry here will be A plus 3A plus B, or 4A plus B. Okay, so for the next one, for the one underneath here, I'll add B and C. So this is equal to B plus C. This entry here will be A plus B plus C, or the same as A plus 2B plus C. This entry here will come from adding 2A plus B plus A plus 2B plus C, and that is the same as saying 3A plus 3B plus C. And this entry here will come from adding this 2, and that is the same as saying 6A plus 4B plus C. Next one, here you'll have C plus D. Okay, here you'll add this 2, so I'll have B plus 2C plus D. Here I'll add this 2, and then I will have A plus 3B plus 3C plus D. Here I'll have the sum of this 2, and that would be 4A plus 6B plus 4C plus D. Okay, and let me complete the last one. That would be D plus E, C plus 2D plus E, B plus 3C plus 3D plus E, and A plus 4B plus 4C plus 4D plus E. Okay, great. So what about this now? Now, as this stands, it will not actually work for the completion of the fractional interpolated values, because the entries in the top row, by the way, all must be 1. So as it stands, that is not really going to work. So what Newton did, he rewrote this pattern in such a way that he wanted to preserve the pattern within each row, each individual row, but he changed the names of the variables. So each variable appeared only in one row. So as you move along, you'll introduce new variables, and those variables will appear only in one row. And then what? And then as you move down the rows, each new row can be described using successively one more variable. So generally speaking, what that means, let me just write this down again. So I'll actually write the rule again. So, okay, as they stand, it will not work. For the completion of the fractional powers, because the entries in the top row, they all must be 1. All must be 1. Okay, so to get around this difficulty, to remedy this, well, Newton Newton rewrote this pattern in such a way that he preserved the pattern within each row, that he preserved the pattern within each row. But he changed the names of the variables, but he changed the names of the variables. So that each variable, appeared in only one row, and only one row. So it appeared nowhere else. That will allow you to create some systems of linear equations and solve for each variable in each row and then fill in the entries. That's the idea. So as we move down the rows, each new row can be described using successively one more variable. All right. So what does that mean? Now let me just rewrite what we said. So changing the names of the variables on each row, we can write the following. So changing the names of the variables would make each row independent of others. Each row independent of others. All right, so what do we mean by this? Let me just do this again. A. Okay, so here I have B. So this is the new variable B, and here I had A plus B, but instead of using the entry A from the previous row, I will say here you have B plus, instead of A, some other new variable. Let me call it C. As you can see in the second row, everything is in terms of A and B, which means that here everything, it'll be in terms of B and C. So I introduce for this row the new variable C. So according to the pattern, this entry should be now 2C plus B, because here I had B as before. 2 times the variable a that appears in the previous one. So since I'm calling that something else, I'm calling that c, but I want to preserve the pattern, I'll call that 2c plus b. The next one would be 3c plus b, and the next one would be 4c plus b. That's fairly simple. Okay, now I cannot call this c because I called c something else on the second row. So instead of c, I need to call that something else. So I'm going to call it d. In this row, c, it is c plus b, where b comes from the previous. So I call this d, so I will have d here, d. So instead of b from the previous row, I need to invent something else, another variable. Let me call that other variable e. Okay? And as you can see, for the rest of the row, everything is written in terms of b and c. That means that here in the same row, everything following this pattern, everything will be written in terms of e and d. So the next one would be you have something else here, which is from 2 rows above. You cannot use something that used 2 rows above, so you are going to introduce one variable and another variable. So for the third row, you are going to introduce 2 new variables, and everything is written in terms of these 2 new variables here. So c was the constant one in this row, so d will be my constant entry, plus something else in terms of these 2 other variables, e and f. So I'll have f, the same as a here, plus 2b or 2e, because I said b here is like e here, plus, well, c here is like d here, plus d. Okay, so the rest is 3f plus 3e plus d, and the next one is 6f plus 4e plus d. Okay, all right, next one is this one. It's called d here, but I used d elsewhere, so I cannot call this d. I'm going to call it g. So I have g, or here we have d plus something else from before. I cannot have something from before, so I need to invent something new. So the d in this row is the g in this row. Okay, so this is something new, so let me call it something new, h. So these 2 are old, but this is new. So I'm going to call it I plus 2h plus g. Here I have the 3 names from the previous entry, but with something else from the previous row. So I cannot have that. I'll need to introduce yet a third variable. So for the third row, or the fourth row here, I'm going to introduce 4 new variables. So I will have k plus 3i plus 3h plus g, and then the next one would be 4k plus 6i plus 4h plus g. What is e here? Since e is used before, I cannot use e. I'm just okay. Cannot use e. I'm going to call it L. So I have L or e. I have something new. Let me call it something new, m. So I have m plus L. I have the d and the e here, so I will have the m and the L, but I have something new here, so let me call that n. N plus 2m plus L. I have the C, D, and E here, but I have something else, so I have to introduce something else. Let me call it P. plus 3n plus 3m plus L. And the last entry, I have B, C, D, and E here, but I have also something else, something new, so I'm going to have to introduce something new. So let me call this Q plus 4P plus 4N, 4L, 4M here plus L. So I'm introducing for each row basically new variables such that these variables only appear in that row, not in other rows. For example, B only appears in this row, nowhere else. D and E, or E appears only in this row and nowhere else. F appears only in this row, nowhere else, and so on. So the point is to get away with the fact that the very first row here must be all ones, so these will not actually work. But we have these other new rules. Okay, so now it's time to actually complete something. So let's just do an example. What do you need to actually complete the table? The table is still here. I'll keep showing this as we go along. Okay. All right, but before we do that, now when we use this table, note the following: that if any entry in the first row is known, I meant to say any entry in the first row is known, then every entry in that row is known, because we're starting with a constant row. So if something is known in the first row, then everything in that first row would be exactly the same thing. If any two entries are known in the second row, for example, if any two entries are known, so if you know any two of these entries, then you can form a system of linear equations and you can find the rest of them. In the third row, if any three entries are known, you can solve for the rest of them and find the rest. In the fourth row, if any four are known, then you can find the rest, and so on. So let me just write this down before we actually do the example. Okay. So using this table now, this new table. Note that if any entry in the first row is known, then the whole row is known. Okay. If any two entries are known in the second row, we solve for B and C and fill in the entire row further. if any three entries are known in the third row, we solve for E, D, F. These are the three new variables that we introduced, and fill in the rest. And so on. Okay, so how do you solve for that many variables in the nth row? By using systems of linear equations. Obviously this is some tedious work and I'm not going to have you complete the whole table, but as I'm going to do an example now, and as homework you should complete some other row, as I'll tell you. Okay, so we'll do an example. So let's compute, for example. We are going to compute the third row. So row 1, row 2, row 3. I want to fill in entries in the third row. Okay? And we are going to use, compute the third row. The third row, using the known values, the known values. 0, I don't know what's after 0, 0, I don't know, 1. So I'm talking about these three values. Do I know these three values? I mean, I know more than that, but I know these three values. So let me try to fill in the missing entries by knowing this. So let's say I'll start from here. So going back to my formula. The third row starts with a D. Okay, so when I say that I'm starting on the third row, it means that this first entry that I know and that I'm going to use is 0. So 0 will be my D here. Okay, so alright, so this means that D will be equal to 0. Third row, first entry, I'm at the third row, I'm starting with the first entry I know, and I'm calling that D. So here D is equal to 0. Okay, so what is the next one? I don't know what's the next one, but I also know not the next one after D, but the second one after D. So I know that is a 0, so I'm saying that this third entry on my third row is actually equal to 0. So I also know that F plus 2E plus D is equal to 0. I don't know what this is, but I know what this is. I know this to be 1. So the next one would be 6F plus 4E plus D equals to 1. And here you are going to solve for F, E, and D. So since D is equal to 0, I can substitute D with 0 here, and I can say that F is equal to minus 2E. So I don't know what E is, but let me work with this other equation. So I have 6 here. I don't know what F is, but F is minus 2E, so I have minus 2E instead of F, plus 4E, I leave it alone. I know that D is equal to 0, so you're saying that this is equal to 1. So I have minus 12e plus 4e, it is minus 8e, it is equal to 1. So this implies that e is equal to minus 1 over 8. So if e is equal to minus 1 over 8, then this would imply that f itself is minus 2 times minus 1 over 8, or equals to 1 over 4. So there I have my 3 variables. And now I can use those to fill in the missing entries. I can use D, F, and E to fill in the rest. Okay, so you can do that. If we do that, and if you do the arithmetic, you will have, in between the two, these two, I should have a minus 1 over 8 if you do the arithmetic. Between 0 and 1, I should have 3 over 8. You do have a formula for it. And okay, so for the next one, you should have a 15 over 8, 35 over 8, and then here you should get a 3 over 8, and you should get a 1 here. Okay, by the way, I don't know if you remember from the previous page, those coefficients are all in terms of plus 1, minus 1. The coefficients of these terms, I mean, are plus 1, minus 1. So this is minus 1, 1, minus 1, 1, minus 1. Okay, so I did this to fill in row 3. So as homework, complete row 2 and row 2 and 4. Okay, and that would be the end of part 2. I shall see you, or you'll hear from me in a minute.